Today we are going to see the relative motion between two particles. And since our objective is to study vehicle reconstruction, we have to keep track of the relative positions and relative velocities of vehicles as they approach each other. So it's important to understand the very basic principles in dynamics. We're going to base ourselves on this presentation based on Hibbeler's dynamics textbook and study first the concepts of the relative position, relative velocity, relative acceleration, and of course we'll end up with the analysis of forces, which would be outside of the kinematic area but would be in the kinetics area. So let's take a look at this. Like I said, relative motion of two particles using a translating axis. So in here we want to understand what translating frames are. We are talking about whether in the picture we see airplanes, but could be two vehicles also. Using translating frames to reference and analyze relative motion. So we would like to do some relative motion, velocity, position, and acceleration, and of course vector and graphical methods. Those are the main things we're interested here. So for example, the velocity, just a little bit of a testing question, thinking a little bit. The velocity of B relative to A is defined as relative of B with respect to A. Is another one is velocity of B minus velocity of A. That's the in vector form. The others none, right? But this one, since the vector addition forms a triangle, there can be at most either magnitudes and or directions of the vectors. What do you think? Vector addition forms a triangle. So can we what can we know? Magnitudes are there. How many unknowns can there be? 1, 3, 2, 4. 4 is not possible. On a triangle, we have to have either two magnitudes and a direction or so. So then to find the magnitude of another vector. So what do you think? There can be at the most, at the most two magnitudes and or directions of the vectors. All right. Let's see. When you try to hit a moving object, for example, the position, velocity, and acceleration of the object must be known. Here, the boy on the ground is at 10 feet when the girl in the window throws the ball at him. So you need to know something about the velocity and the position, of course. If the boy on the ground is running at a constant speed, how fast should the ball be thrown? That's another application, for example. So this is relative position and velocity. So these are the kind of things that we see. When a fighter jet takes off the land of an aircraft carrier, the velocity of the carrier becomes an issue. Why is that? Because the plane is part of the carrier for a while. So you not only have the velocity of the carrier to take care of, but the velocity of the plane with respect to the carrier. So if the carrier is going, let's say this way, yeah, and you are taking off this way, what happens on takeoff? The velocity of the plane is not exactly just the velocity of the plane. It's the velocity of the plane, and it has the velocity of the carrier to contend with. So if you take it in the same direction as the carrier is going, then there's no relative velocity. But if you do it this way, then it is. See, if it travels forward the velocity of 50 kilometers per hour and the plane takes off at horizontal airspeed of 200 kilometers per hour, how do we find the velocity of the plane relative to the carrier? So this is for the airplane A is easy, would be the difference, but for the plane B would be also a difference, but vector difference. And of course, the wind also comes into picture. Here another problem. The two particles A and B, yeah, with respect to some fixed frame, that would be RA and IB. The position of B relative to A is pi. So the position of B relative to A is over here, is this vector. So R sub B minus A sub A is the relative position between B and A. So if you have R sub B is 10I plus 2J would be a vector, and RA is 4I minus 5J. When you have the components, you add or subtract in the directions, and that would be the relative velocity. This is very important in accident reconstruction. Relative velocities, because it's also important to understand that relative velocities deal with the change of direction. When a vehicle collides with another, for example, it was going this way, and now it goes this way, as it was impacted from the side. Well, this is the relative velocity of B with respect to A. Okay, this would be a, think of the velocity difference also equivalent to velocity change, or the change in the, in this case, changing the velocity vector. Velocity v and velocity v are called absolute velocities, and velocity v with respect to a is called the relative velocity. In this case, you see this velocity of v with respect to a is v sub v minus v sub a. But if you say velocity of a with respect to v would be the same but with the inverted sign, because this would be velocity of A minus velocity of B. So if B with respect to A was in this direction, minus B with respect to A would be in the opposite. Relative acceleration. If we change the velocities, including the relative velocity like we have in here, basically we will have to differentiate these vectors. If we don't have omega involved, in other words, they're not turning and translating, then it would be just the changing length. not consider the rotation. Therefore, this is true, that the acceleration of A and then the acceleration of B can produce a relative acceleration of B with respect to A if you differentiate, if you subtract the acceleration of B minus the acceleration of A. So the acceleration of B with respect to A is acceleration of B minus acceleration of A. This vector sum, I think, is important to remember that. I'm just going to say remember. This is a vector sum. Or subtraction, yeah? That's important. Okay. This is what I just made a comment a moment ago. Remember, it's vector sum. The velocity vector b is equal BA plus B of B with respect to A could be written in Cartesian vectors and the resulting scalar equation solved for up to two unknowns. Okay, so two unknowns. Alternatively, vector problems can be solved graphically by using trigonometry. This approach usually makes use of the law of sines and the law of cosines. Yeah, because you have to solve triangles. Could the computer design system be used to solve this type of problems? The answer obviously is yes. So let's review the laws of sines. The law of sines, if you have A, B, and C triangle in here, this is just a solution of triangles, but since the vectors have magnitudes and they have directions, then we can build a problem giving obtain what is unknown by using the calculations graphically, putting the vectors and then doing vector addition graphically. The law of sines, it says that the opposite side on a triangle is always proportional to the sine of the angle. That is something that we know from our trigonometry class. So A is to the sine of A, as B is to the sine of B, as C is to the sine of C. And that's what you see here, the law of sines. The laws of cosines, it says that if you have, like in here, you have A, and then you have B over here, that, and then there's C, that A squared is B squared plus C squared minus 2 cosine of A. Okay, this is the velocity 2. Now the velocity is B sub 2 squared plus A squared. No, B squared is A squared plus C squared plus AC cosine of beta. Now C A squared plus B squared is equal to 2B cosine cosine of c. Always remember this cosine term is the angle that the two forms, like A and B. This would be C. A and C is B, and C and B is A. Right? So far so good. Those are the two laws that we use. So a lot of times in accident reconstruction, you might use and draw the vectors to scale and use this method to find others. For example, in here, let's just try to solve some problems now. These are two airplanes, but they could be two cars. Okay, the question is, the velocity of A is 600 kilometers per hour. The velocity of B is 700 kilometers per hour. The question is, what's the velocity of B with respect to A? How should we go about finding that? Huh?
Would it be 100?
That would be if it would be algebraic, but not here because they are vector sum. See, we will have to write the vectors A and B in Cartesian form and then add them graphically. Graphical method, you draw the vectors A and B from a common point, apply the laws of sines and cosines, and of course you can get that also. Here's an example. Vector method. Yeah, here's 35 degrees. So if you look at the vector method, 6 cosine of 35, I minus 6 cosine of 35, j. And then b is minus 700 I. You see how that is considering the fact it's going totally in this opposite direction. And then you have velocity of b with respect to a. See, we add the vectors in here. Okay. So if you use the components there to do the sum, then you end up with a vector that says minus 1191.5i plus 344j. And then if we take the magnitude of this, which is what's happening here, you have 1240.2. And then you have to calculate the angle theta is arctangent of 344 divided by 1192, 16 degrees. So here's an example using the law of cosines now. You have the velocity of B here and the velocity of A. This line that joins the two is the relative velocity. Okay, so if you apply this, you will get the velocity of A is 1240. which is what we obtain over here before. Okay, so it's just application of the law of cosines. And using the law of sines, so law of sines or law of cosines, whenever you have this triangle. Okay, let's go and try some examples now. So for that, I'll refer you to the other presentation, and we are going to go to example. Let's see. Let's do an example of this. Here's an example of this kind of motion in here. A train is traveling at a constant speed of 60 miles per hour. Like I say, this could be vehicles also. Crosses over a road, as shown in figure 1245. Says if an automobile A is traveling at 45 miles an hour along the road, question is determine the magnitude and direction of the relative velocity of the train with respect to the automobile. Another way of saying this is the relative velocity of the train having, you could say, the automobile as a frame of reference. That's another way of illustrating this. So if you look at the first solution that says vector analysis, the relative velocity of the train with respect to A is measured from translating the x prime and y prime axis attached to the automobile. Okay. So v sub r is v sub a plus the velocity of the train with respect to the vehicle. So since velocity of the train v sub r are known in both magnitude and direction, the unknowns becomes x and y components of v sub r with respect to a, v sub t with respect to a. So if you use x and y axis and the Cartesian vector analysis, we have velocity of the t, so v of t is velocity of the train, is velocity of a plus the velocity of t with respect to a. Okay, so v of t in this case is velocity of a plus velocity of t with respect to a. So you have the velocity of t with respect to a. This is to get the magnitude of that vector, but the vector itself would be here. Okay. If you take the derivative of this, you can continue and say y is equal to 10 meters, x is determined and calculate the velocity here. The acceleration is I think we have the answer here. Magnitude of the train with respect to the automobile would be the magnitude of the relative velocity, and that would be the answer. Okay, let's try this other one. Here you have a plane A in this figure is flying along this radius of curvature of 400 kilometers. So whereas plane B is flying along a circular path having a radius of curvature that we're giving in there. Sorry. Well, the question is determine the velocity and acceleration of B as measured by the pilot of A. This is good. It's establishing a reference point. Yeah. Is as you would say is as if it is observed by somebody standing on A. So we're trying to establish the velocity, the relative velocity. All right. So here's how it goes. The x and y axes are located in an arbitrary fixed point. And since the motion relative to the plane A is to be determined by translating frame of reference is attached to it, figure 1244, applying the relative velocity equation in a scalar form since the velocity vectors of both planes are parallel at the distance known. So it's as shown. So the velocity of B is the velocity of A plus the velocity of B with respect to A. Okay. So in here is the vector, and then the velocity of B is this, but because we have it in the same direction, so this will be the relative velocity between the two. And this is true too with vehicles. You calculate the relative velocity if they're going in the opposite direction, or if you're going in the same direction, it would be the velocity minus the velocity of the other. But what's important to remember is, in general terms, it's not an algebraic sum, but rather a vector addition. Okay.